Hello everybody. Um, in this video we will be focusing on the fundamental theorem of calculus. So we will introduce this theorem and then we will apply that to compute integrals, to compute definite integrals. The fundamental theorem of calculus shows the connection between the two main concepts of this course. One of them is the concept of the derivative, which is the rate of a function, and then the other concept is the concept of the definite integral. So here is the fundamental theorem of calculus. If small f is continuous on an interval from a to b, this is a closed bounded interval, and if capital F is any antiderivative of small f, then the definite integral from a to b of f of x dx is equal to a quantity which is denoted by this symbol. So this symbol here represents a quantity which is f of b minus f of a. So the fact capital F is an antiderivative of small f, so it means that small f is the derivative of cap f, or small f is the rate of cap f. So basically this theorem tells us that if we integrate the rate of cap f, so small f is the rate of cap f, if we integrate the rate of cap f from a to b, then we get the net change in the value of cap f. So f of b minus f of a, that's the net change of the value of cap f over this interval. And another way of saying this is that if we are integrating small f of x from a to b, then the first thing we do is we compute the antiderivative of f. So we find one antiderivative, capital F of f, and then we evaluate capital F at a and b, and then we take the difference, f of b minus f of a. Alright, so let's apply this. So let's say that we want to find the integral from 1 to 3 of 4x cubed minus 7 dx using an antiderivative. So what's the antiderivative of 4x cubed? Well, that's 4x to the 4 over 4, which is going to reduce to x to the 4. And the antiderivative of negative 7 is negative 7x. And when you take the antiderivative, you get a constant of integration, but I'm not writing it here because we don't need to. Even if you write a plus c here, that's going to cancel out when we subtract here. So now we plug in, so we found an antiderivative of this integrand, and now we plug in 3 for x, we get 3 to the 4 minus 7 times 3, and then we plug in 1, we get 1 to the 4 minus 7 times 1, and then we are subtracting. So this is the antiderivative evaluated at 3 minus the antiderivative evaluated at 1. And if we do the simplification, then we end up with 66. So 3 to the 4, that's 81. This is 21. So 81 minus 21, that's 60. And then this is 1 minus is 7, which is minus 6. And then there is another minus here, so that's plus 6. So we get 66. Now we're going to evaluate the same integral here again, but this time we're going to use a different antiderivative. So this time the antiderivative again is x to the 4 minus 7x, but we can add any constant to it, and still we get an antiderivative. So if I add a constant here, then let's say 5, then what do I get? Well, Again, we evaluate the antiderivative at 3 and at 1, and then we subtract. So if we do that, evaluated at 3, we get this. Evaluated at 1, we get this. Right? 3 to the 4 minus 7 to the 7 times 3 plus 5. This. Now notice that 5 cancels out. No matter what constant I write here, right? So it will cancel out. So generally when we find the antiderivative, we have a plus c, the constant of integration, but it will cancel out right at this step right here. So there is no need to write plus 5 or plus c when we are doing these definite integrals. So the answer is still coming out to be 66. So from now on, when we find the antiderivative to compute the definite integral, we are not going to write the constant of integration because it is unnecessary. The constant of integration always cancels out at this step. Okay, so the choice of the constant c makes no difference, so we are free to use the 0 for c. All right, so let's evaluate the definite integral from 0 to 4, x cubed minus 3x dx. So we need to find the antiderivative here. So the antiderivative of x cubed would be x to the 4 over 4, and the antiderivative of negative 3x would be negative 3 times the antiderivative of x, which is x squared over 2. And then we have to evaluate the antiderivative at 4 and at 0, and then we need to subtract. So plug in 4. When we plug in 4, we get 1/4 4 to the 4 minus 3/2 4 squared minus 1/4 0 to the 4 minus 3/2 0 squared. And do the arithmetic and simplify, we get 40. So clearly we get 0 here. Here we get 4 cubed, which is 64, and here we get 24. So 64 minus 24 here would be 40. Well, here I want to show that the integral from 0 to 6 of x squared dx is equal to negative integral from 6 to 0 of x squared dx. So notice that all we are doing is we are switching the limits of integration here, and it turns out that generally when you can switch the limits of integration by introducing a negative, by multiplying the integral with the negative 1. So left hand side, the antiderivative is x cubed over 3, 6 and 0, plug in 6 and 0, we get this 72. And on if I look at the right hand side, the antiderivative would be, well, negative here and then x cubed over 3, plug in 0, 0 is now the upper limit, 6 is the lower limit, plug in 0, plug in 0, plug in 6 and subtract, and we still get 72. So these two sides are equal. So generally keep in mind that you can switch the limits of integration by introducing a negative sign in front of the integral. All right, so let's look at the integral from negative 1 to 2, 6x to the 5 minus 1. The antiderivative of 6x to the 5, what's that? Well, it will be 6 times x to the 6 over 6, which reduces to x to the 6, and then the integral of 1 is just x. So I get x to the 6 minus x as the antiderivative of this integrand. Now we plug in 2 and negative 1. If I plug in 2, we get 2 to the 6 minus 2. If we plug in negative 1, we get negative 1 to the 6 minus 1. This would be 2 to the 6 is 64 minus 2, so that's 62. Here, negative 1 to the 6 is going to be positive 1 here, and then I get a positive 1 here, so altogether I get a 2 here. So 62 minus 2, that's 60. Let's say we need to evaluate the integral from 2 to 4 of 2 over x cubed dx. So to find the antiderivative of the integrand here, we're going to rewrite that as 2 times x to the negative 3, and then apply the power rule to find the antiderivative or the indefinite integral. So it'll be 2 times x to the negative 3 plus 1. So that's negative 2. So x to the negative 2 over negative 2. And then finally we need to plug in 4 and 2. So simplifying this, we are getting negative x to the negative 2. We can write it as 1 over x squared. Alright, so after this simplification, plug in 4, we get negative 1 over 4 squared. Plug in 2, we get negative 1 over 2 squared, but we have to subtract. So this is subtracting one from the other. Here we are getting 1 over 4. Here we are getting 1 over 16. So negative 1 over 16 plus 1 over 4 here. And at the end we get 3 over 16. Okay, so let's look at another example. So here we have the integral from 0 to 1 over 3x plus 5 dx. So I need to find an antiderivative of this guy first. So what I'm going to do is first find the indefinite integral of 1 over 3x plus 5. And we're going to use the u substitution. So taking u to be 3x plus 5, we know that du would be, if u is 3x plus 5, then du would be 3 dx, and du would be 3 dx, and so dx would be 1/3 du. So we substitute dx by 1/3 du, so 1/3 du, and this would be 1 over u. So 1/3 being a constant, we can always keep it outside of the integral. Now integral of 1 over u, we know that is ln of absolute value of u. So we get 1/3 times ln of absolute value of u, and then we add a plus c. And finally, we substitute u with 3x plus 5 again. So you get 1/3 ln of absolute value of 3x plus 5 plus c. So that's the indefinite integral. Now, to compute this definite integral, though, we don't really need the c. So now we're going to apply the so we got that 1/3 ln of absolute value of 3x plus 5 is the antiderivative of this guy. Now we plug in the limits of integration. So plug in 1, we get ln of 8. Plug in 0, we get ln of 5. So we get 1/3 ln of 8 minus ln of 5. And by using one of the log properties, we know that this is the same as 1/3 ln of 8 over 5. Now, this same definite integral right here, now I'm going to do it a little bit differently, and then that's going to tell us, that's going to lead us to the substitution method for definite integrals. So again, we're looking at the same integral as in the previous example. So integral from 0 to 1 over 3x plus 5 dx. So directly, without writing indefinite integral here, I'm going to substitute 3x plus 5 by u, and then du would be 3 dx, and 1/3 du would be dx. So within this integrand, I'm going to get 1 over u, and this would be 1/3 du. So now we are also going to change the limits of integration. So notice that when x is 1, what is u? Well, u is this. So when x is 1 here, u would be 3 times 1 plus 5, which is 8. And when x is 0, u would be u would be 3 times 0 plus 5, which is 5. So this definite integral here is the same as 1/3. So 1/3 du is replacing dx, and then u is replacing 3x plus 5, so you get 1 over u. And then the new limits of integration we get is 5 to 5 and 8. Okay, now we get this. Now because we changed the limits of integration, we adjusted the limits of integration for u, we don't need to go back to x. So right now we can plug in 8 and 5. So we get 1/3 ln of 8 minus ln of 5, which is 1/3 ln of 8 over 5, as we got before. Okay, so this method that I apply, that's basically the substitution method for definite integrals. And we're going to stop the video here because I don't want to make this too long. But in the next video, we will present the substitution method for definite integrals and then apply that and solve a bunch of problems. All right, so see you then.